Hello, this is Professor Elliott. Welcome to Capacitor Charging and Discharging. Okay, these are the universal curves that we're going to use to solve and calculate and predict the charging and discharging behavior of a capacitor. And we will shortly use the same curves to do likewise when we look at inductors. Okay, basic charging circuit. Our initial assumption is that the capacitor voltage, Vc, we're going to assume it's equal to 0 volts. So the capacitor is initially discharged. And then with switch 1 closed, we will have a current path all the way down, like that, to start charging the capacitor. Just a little side note is that the current flow, there's current flow here, there's current flow here, and there's current flow, of course, here, but there's no current flowing through the capacitor itself because the plates in the capacitor are separated by an insulating dielectric. And the current flow is caused by just the movements of charge, or just electrons. So just a side note, the current doesn't actually flow through the capacitor, or we typically sort of say or pretend it does. It's actually quite not true, but anyway. So ignore switch 2 for now. We use that when we discharge. And so with the capacitor starting to charge, then let's look at the behavior that we would expect to see. Okay, so again, the initial assumption, is that the capacitor is uncharged. When we close switch 1, current then flows through the resistor, and then the capacitor charge starts to increase, and the capacitor charges along an exponential curve, which is what the graph we looked at in the beginning is telling us. Oh, just by the way, so this here is the exact mathematical equation for the graph. So if you were to plot many points using this equation, you would come up with the universal curve graph. Okay, so again, the capacitor as it's charging, then we know we have voltage E, okay, whatever that number is. And then depending on where we are on the curve, there's going to be a voltage Vc on that capacitor. Now, because this is a series circuit, we know by Kirchhoff's voltage law that the sum of the voltage drops around the loop must always add up to the source voltage. So therefore, we can solve for the resistor voltage if we know the capacitor voltage and source E. Okay, and that's just what that is telling us here. Okay, when we're discharging, then switch 1 here, notice how it's now open, and we've now closed switch 2, so the charge on the capacitor is going to bleed off now and go that way. And notice that because the current is going the other way through the resistor, the voltage now has a negative polarity. Okay, when you're discharging, again, this is the exact exponential equation. And and we'll talk more about later, but that's basically the basic operation. Okay, this is the saying that the current is going opposite way through the resistor when discharging, so the voltage must have the opposite polarity. Okay, so that's what this note here is saying. Okay, so let's look at an actual example with some numbers, and we're going to use the universal curves to determine the capacitor voltage and currents at various points. The time constant for a capacitor, one time constant is the product of the resistance here times the capacitance there. So if we put that into the calculator. One time constant is equal to 2K times 200 microfarads. Put it all in base units, you'll get seconds. Convert it to milliseconds, you get 400 milliseconds. So that means for every time constant change in time, right, that represents 400 milliseconds. So that means that two time constants would be 800 milliseconds. Three time constants would be 1.2 seconds, and so on. So at time equals 0 means at the instant we close switch 1, okay, assuming the capacitor is initially discharged, then the capacitor voltage is 0. Then by Kirchhoff's voltage law, the source voltage has to be accounted for somewhere, and that's going to be across the resistor if the capacitor voltage is 0. So therefore then we have 24 volts on the resistor, and the current through the resistor, simply Ohm's law, is VR divided by R, which is 12 milliamps. So this is the maximum current at the instant we close the switch to start to charge. Okay, so that 12 milliamps is going to occur right there. All right, so this curve here is the capacitor charging. This curve here is the resistor charging, and it's also the resistor current. Okay, so if we start the capacitor off at 0, then one time constant later, which for these values is 400 milliseconds, then the capacitor will have increased, if you look right there, to approximately 63%, or 63% of E, or 63% of the 24 volts. Okay, which is going to be, calculator. So if we take 24 volts times 0.63, that equals 15.12. So that means at one time constant, we can say then that VC equals 15.12 volts. Okay? All right, next one. Okay, so at two time constants, so just an FYI, this would be 2 times 400 milliseconds, so that would be 800 milliseconds. We're going to go to the curve, and we're going to say that is 20.64 volts. Once we know the capacitor voltage and we know E, we subtract using Kirchhoff's voltage law to get the resistor voltage, and then in Ohm's law to divide to get the current. So if you go here to two time constants, okay, again this is the capacitor charging graph, go to that point right there, and that's about 86% of E. Okay, and that's where I got this number here, and then once you have the capacitor voltage, you simply subtract to get the resistor voltage. All right. Okay, so at 3 time constants, okay, let's go to the graph. So we are way down here. At 3 time constants, then we are at about 95% of E. Go back. So 95% of 24 is about 22.8. And then using Kirchhoff's law, we determine the resistor voltage to be 1.2. So just remember that at all points along the curve, then the sum of VR plus VC must be equal to E And for our little example here, it's always equal to 24. And once you know VR, then you can simply divide by R to get the current. So if you go to the graph, you see when at the instant we close the switch here, we had the maximum current, and then as the resistor voltage decays this way, the current must decay, and as the resistor voltage decays, the capacitor voltage grows, so that at the end of the charging process, we'll see after 5 time constants, then the resistor is going to have 0 volts, 0 milliamps, and the capacitor will be charged to 24 volts. Okay. 4 time constants. Okay, so we're way over here. We're almost to the end. So off the graph, I'm saying the capacitor voltage is about 98% of its final. Okay, so that's 23.52. Subtracted from E, 0.48, divided by R is 20.24 milliamps. Okay. Now at 5 time constants, okay, the capacitors by the graph is about 99% charged. You can just say the capacitor voltage is 24 volts, and by standard convention, it's assumed that capacitor is fully charged or fully discharged after 5 time constants. Now, in actual fact, this voltage won't actually reach 24. It's about 98.5 to 99%. I mean, something like that, because the dielectric isn't quite perfect, so it's always bleeding off charge. So, in actual fact, VC will be slightly less than 24, and the resistor voltage VR will be slightly greater than 0. But you can just approximate it, and it's a good approximation. There's nothing wrong with it. To say after 5 time constants, VC is 24 and VR is 0. Of course, IR, the current, is also 0. Okay, capacitor discharging. So in this case, have a new little diagram, and when we're charging, we're going to put the switch in position C, so then we get current, so you can go like that. But now that we're discharging, then we move the switch to position D for discharge. The current's going to go the other way. It's going to go back like this. Okay, so use the universal curves to determine the capacitor voltage. Resistor voltage and the current, okay, at various points along the curve, the same as we did for the charging. And we're going to assume that the capacitor is initially fully charged, so we know we have a good solid known starting point. Okay, and just note that about the current direction change, which we've talked about before. So at time equals 0 seconds, so in other words, that's the time we're moving the switch from charge to discharge. So if the capacitor was initially charged to 24 volts, the nanosecond after moving the switch, it's still at 24 volts. And the resistor voltage is 24. Now this can be confusing, so I'm going to go back to the diagram, two slides back. So if I just go and just want to clean this up a bit. I'm sorry. Okay, let's try that. Okay, so would you agree that this point here and this point here, down here, are the same points? It's just a wire and a switch, so electrically the same points. So is not the resistor and the capacitor in parallel? Okay, they are. So therefore, then the capacitor voltage VC surely it must be the same as the resistor voltage VR. Okay, and that's why I'm making that statement there. The resistor current is equal to the resistor voltage divided by the resistance, so it's 12 milliamps. Okay. So at one time constant, let's go to the graph. Okay, so we're starting off here. VC was 100%, or E, or 24 volts. After one time constant, then it's decayed down to this point, like that, like there, which I'm saying is about 36%. So 36% of its maximum initial voltage is about 8.64. And then because the resistor and capacitor are literally in parallel, the resistor voltage is 8.64. Divide by the 2K to get the current, 4.3. Okay, two time constants. So the capacitor voltage continues to decay. So we're down here now. So that's about 14% of E. So 14% of the 24 is 3.36. And because the resistor and capacitor again are in parallel, the resistor voltage is 3.36. Divide by the resistance is 1.68. So this curve here, when you're discharging, is the capacitor discharge, resistor discharge, and resistor current. So it's all in the same curve. Three time constants. Okay, so we're down here. Okay, we're there on the graph. Okay, so that's about 0.05. So it's about 5% of the 24, just the 1.2. Again, VR is 1.2. The current is 0.6. So we're expecting to see the VR, VC, and the current decaying as we go down, and that's what we have. Four time constants. So we're almost done. So 4 time constants here. It's about 2% of its maximum. Okay, so that's about 0.48, 0.48, and about 2.24 milliamps. After 5 time constants, again, this is at the extreme bottom of the graph, we can just simply say VC and VR and IR are all 0. That would be perfectly fine. So you could make the standard assumption, just make that 0, make that 0, and make that 0. Okay, that would be just fine. Okay, thank you for watching, and I hope this was beneficial to you. See you all in class soon. All right, have a great day. Bye-bye.